I thought that today, rather than talking about Interstellar, I will answer questions about Interstellar if you wish afterwards. I'll even answer a little bit about the next movie that I'm working on. But I thought I would give you some overview of my own life in science, because I know that some of you at least are working toward careers that may involve science. And you might find some of the things that I experienced over my career interesting, maybe even useful. And so that's what I will be talking about. When I was a small boy, I lived in the Rocky Mountains in North America. I watched the snowplows pile snow to unbelievable heights, 6 times as high as I was tall. So naturally, I wanted to be a snowplow driver when I grew up. But then, when I was 8 years old, my mother took me to a lecture about the solar system, and I got hooked. And so I abandoned snowplows and decided I wanted to be an astronomer. That is, until I was 13. When I was 13, I read a book by the physicist George Gamow, a book that changed my whole life. It was called 1, 2, 3, Infinity, and it described both physics and mathematics and the wonderful questions that physicists were struggling to understand, including the birth of the universe. And I just fell in love with physics and its application as a tool for understanding the universe. And so I wound up working in my career as a physicist who works on astronomy, partly, but partly on other areas. When I became a mature physicist 13 years later, I wrote my first technical paper, and it was about the Big Bang and the physics of how the universe, the early universe evolved, what was going on in the early universe. And I mention this simply because George Gamow, who had written 1, 2, 3, Infinity, read my paper and sent me a letter asking some questions about it. And I was overjoyed because he was my hero. And so I responded, I answered his questions, and I told him in my response that I was a physicist because of his book, that I had read his book 1, 2, 3, Infinity 6 times as a kid. He responded immediately and sent me a copy of 1, 2, 3, Infinity in Hungarian, inscribed to my dear colleague. It was great to be called a colleague at that point. To my dear colleague, Kip Thorne, so he would not be able to reread it a 7th time. Now, Gamow's impact on me was so great that I felt I owe a huge obligation to pass on to the next generation and generations after that the message of how beautiful and how powerful science can be. And so that's what I've tried to do, first with a book that I wrote called Black Holes and Time Warps, Einstein's Outrageous Legacy. It's old by now, 1994, so it's a little more than 20 years old. But still, it's a book that describes the history of the development of our ideas about warped space-time and the ideas themselves. But then more recently, I tried to pass this on to the next generation with the movie Interstellar, which Christopher Nolan and I together designed to be a lure to entice people of your generation into becoming intrigued about science. And then my book, associated with that, The Science of Interstellar, as a hook to try to get you hooked on science when you read the explanations of the unbelievably weird things that you see in the movie Interstellar. And so I'll be happy to discuss that if you wish in the question and answer period. But I want to go on and talk about other things in my career. I should say that was the only way I knew how to spread George Gamow's message of the beauty and the power of science to an audience of 100 million people. Only Hollywood can reach 100 million people, which we did with Interstellar with that kind of a message. So returning to my youth, I went to Caltech as an undergraduate student in 1958, and I quickly discovered that I was not as smart as most of the other people in my class. My mind worked a lot more slowly. And so I had to struggle, and I struggled really hard for the first year and a half of undergraduate school. And I had to develop ways to compensate for the fact that my mind was slower. Being slower doesn't mean you can't think as deeply. The goal was to think more deeply than other people, even though I was slow. And a key piece of this that enabled me to ultimately succeed despite being slow was that I made up notebooks for myself in which I wrote down in my own words and my own versions of the equations all the important ideas that I was learning. And I also put in my own proofs by my own approach of the important results about physics or mathematics. And I've continued to do that to this day. What I'm showing you up here is a notebook not from my student days, but from a few years later when I had come back to Caltech on the faculty. But I still do this up until today. And I find this enormously useful in terms of mastering material. I need to get it into my own way of thinking. During the summers as an undergraduate, I worked as an assistant engineer at the Thiokol Chemical Corporation, helping to design solid propellant rockets like the rockets that propelled the space shuttle that took the astronauts into space to the space station. As we blew up engine after engine due to defective designs, I learned an awful lot about what can go wrong, about physics in the real world, particularly about turbulence, as the turbulent gases inside that rocket engine ate away into the casing of the rocket engine and blew a hole in the side of the rocket engine. And learning about physics in a real situation like that as an engineer was tremendously important to me later on when I got involved with gravitational waves, as I will describe. Also important were my experience as a graduate student at Princeton University. I went there to work on theoretical physics, but I spent much of the first year that I was there doing an experiment in nuclear physics, firing protons that came out of a cyclotron up against rhodium atoms. This is just an atom, a heavy atom with an atomic nucleus, to explore the properties of rhodium. A fairly routine nuclear physics experiment, but of some importance in that era. But just getting the hands-on experience with doing a real experiment, just like I had about engineering previously, again turned out to be very important to me. I didn't know what I was going to do with this at the time. I didn't know I was going to get involved in an experiment to look for gravitational waves, but I just figured that if I got additional experience more broadly, that would likely pay off at some point in the future. In the same vein, I spent a lot of time in an experimental physics group, an experimental gravity group that was headed by Robert Dicke. In the period when Dicke conceived of the idea of looking for electromagnetic radiation, microwaves, left over from the Big Bang, he set up his experiment, and he was in the midst of pulling it off when, just down the road, he learned that this radiation had been seen already by people at Bell Labs. They got the Nobel Prize. He didn't. He deserved it. He was the one who knew what they had found, and they didn't know about it. That's another story. But the point was, for me, that I was immersed in an experimental gravity group, and I saw the planning of experiments. I saw the intellectual process that went into designing experiments and deciding what experiments were worth doing. And then, of course, at Princeton, the most important thing for me was working with John Wheeler, who turned out to be my Ph.D. mentor. John, or Johnny, his wife told me the day after I got my Ph.D., and I phoned her up and I said, "Can I talk with Professor Wheeler?" She said, "Now, Kip, you got your Ph.D. yesterday, now you can call him Johnny." And so Johnny, as I can't learn to call him, was a very insightful man who was in the process of revolutionizing relativity theory, which is Einstein's theory of warped space-time. And he was telling us that there were fascinating issues in relativity theory involving things like black holes and wormholes. So let me just show you a modern-day rendition of a universe that has a lot of black holes and wormholes. This is an rendition by an artist, Leah Halloran. In my current life, I'm 76. I now do things that I like to do for enjoyment. I'm doing a book with Leah Halloran that are her paintings of things on the warped side of the universe, like black holes and wormholes, and my poetry. You didn't know I wrote poetry. I didn't know it either, but I'm trying. Anyway, so this is one of her paintings of black holes and wormholes. And you see up here, so a wormhole is a sort of a tunnel through the fifth dimension. Why the fifth dimension? Well, let me explain. In here I have removed one of the three dimensions of the space that we live in from the picture because I can't possibly visualize 5 dimensions all at once. So I've removed one space dimension. I've also removed time. We live in a 4-dimensional universe, 3 space plus 1 time. In the movie Interstellar and in real physics, and possibly in real physics, there is a 5th space dimension. And that's this region out here, also called the bulk by physicists. And this wormhole reaches through the bulk from one location in our universe that has one space dimension removed to another location. So this looks like a Dr. Seuss drawing. It is a two-dimensional rendition of our universe. Our universe does not have this many black holes and wormholes. It would be very interesting if it did, but this is just to explain the idea. This is a black hole. It looks like a failed wormhole. Down at the bottom, it has a singularity that is a place where the laws of physics break down, and therefore is very interesting. But the key point of this was that John Wheeler then was telling us that we should study how warped space-time with things like black holes and wormholes behaves when it's highly dynamical, when time, the rate of flow of time is oscillating wildly, when the shape of space is oscillating wildly. And what do Einstein's equations of relativity predict for that? We know today that nonlinear effects are tremendously interesting. They are related to tornadoes, to turbulence. They are related to modern technology, modern optical technology. A TV picture wouldn't work without nonlinear effects in optics. What kind of nonlinear effects occur in highly dynamic situations in warped space-time? I'm going to return to that because that became for me a driving force. How do we study this? I would like to know how warped space-time behaves when it is in a storm, like a storm at sea. How does it behave? That became an intellectual driving force for me as I moved on in my career. In 1966, I returned to Caltech, and I built for myself a research group similar to the research group I had been in, the theory research group I'd been in with John Wheeler at Princeton. This is a picture from just a few years later of my research group and a number of visitors, including Stephen Hawking, who's obvious there in the wheelchair. And that's me. I now have a beard and long hair. It's the 1970s, sitting there beside Stephen. As I set up my own research group, the key thing that I realized, having watched John Wheeler at Princeton and Bob Dickey at Princeton, was that students are capable of doing really great research if they have a mentor who points them in an interesting direction. And so, in fact, what happened was that I built a research group and pointed students in interesting directions, and they did far more important research over the lifetime of my research group than I did. The greatest discoveries that came out of my group came from the students and not from me, but students inspired by me and by senior visitors like Stephen Hawking. So, for example, Bill Press there, who's beside those words, Bill Press, he was a student who showed mathematically with Einstein's equations that black holes can vibrate, the first evidence of dynamic behavior of warped space-time. And then Saul Tucholsky, the one up in front, he developed the full mathematical description of how black holes vibrate, again using Einstein's equations. And so we were off and running in this small area of beginning to understand geometric dynamics. But I use that as an illustration of the great work that my students did over the years. This is just an example. If you had a small black hole, and so this is the actual shape of the warped space-time around a fast-spinning black hole. It's shaped like that. Again, I've removed one dimension, so you're now just a two-dimensional being, and I'm looking in from the fifth dimension of Interstellar, from a higher dimension. And that's a warped shape that looks like that trumpet horn. And there's a little black hole orbiting around the big black hole, and as it goes around, it excites vibrations of the warped space-time of the big black hole. And so you see these waves beginning to form around the big black hole, which are so-called gravitational waves, but they're waves in the shape of space and waves in the rate of flow of time that are propagating outward into the universe. And so down to the right, I show those gravitational waves. It was Albert Einstein in 1916 who predicted the existence of these gravitational waves and told us that in his paper, in effect, he said, these waves are so weak that you're never going to detect them. The human race will never detect them. It is basically the subliminal message. He didn't say it in quite that bald of words, but that was the message. But then Joseph Weber in the 1960s at the University of Maryland had the insight to realize that first, two things had happened. First, we had learned about the existence of black holes and neutron stars, which would be far stronger sources of these gravitational waves than anything that Einstein knew about. And the second was there was new technology developed in that half century since Einstein. And so he had the guts to say, okay, I'm going to go out and search for gravitational waves. He failed by the techniques that he used. But he was an inspiration for me and for others. I went walking with him, hiking with him in the Alps, in the French Alps for a few days, and was really inspired talking with him. And so in 1972, together with Bill Press, that graduate student who was the one that showed the black holes can vibrate, together with Bill, I wrote the first of what would ultimately be a long series of technical articles describing a vision for the science that we could do with gravitational waves if we could just detect them. What kinds of things would we see? What kinds of things would we learn? And what did this insight about what we might go after, what did that imply for how you would go about detecting gravitational waves? Simultaneously in 1972, Ray Weiss, who was at MIT, and whom I had known in Bob Dickey's research group when I was a graduate student at Princeton, Ray Weiss published is the wrong word, he wrote a technical paper in which he described his invention of a particular kind of gravitational wave detector. And in this technical paper, well, let me just talk about this detector for a moment. So what you have is you have 4 mirrors that hang from overhead supports by wires. And when a gravitational wave comes along, the wave consists, when it arrives here, of a stretching and squeezing space. Equivalently, inertial reference frames here and there move relative to each other, which they cannot do unless space is stretching and squeezing. And so these mirrors that ride on the inertial reference frames remain at rest locally in an inertial reference frame. They move back and forth at frequencies high compared to the 1 cycle per second swinging frequency of a pendulum. They will move back and forth. And so these mirrors move apart while those mirrors move together. These move apart then, and those move together. And a technique called laser interferometry, which I won't go into, is used to monitor those mirror motions. And Ray then identified all the major obstacles, all the major sources of noise that you might face if you were to build such a detector. He estimated what the level of the noise would be after you had used, well, he also described ways to deal with each of these sources of noise. And he told us, made an estimate of what the level of the noise would be after you had done everything you could to reduce it, and concluded that the resulting level of noise would be low enough that if you made this device be several kilometers in size, that you had a real possibility to detect the gravitational waves that I and other theorists were predicting. So this was quite exciting, but not to me. In fact, I wrote a textbook, and that same year I was writing the textbook, I heard about Ray's ideas. I had not studied his paper. And in this textbook, I had the temerity to pronounce a judgment that this approach to looking for gravitational waves was not promising. Why? Well, it's because of the small motions. If the separation between these mirrors is a few kilometers, as it is in the gravitational wave detectors that Ray and I and colleagues ultimately built, then how much do the mirrors move as a gravitational wave goes by? The realistic gravitational waves that I was predicting would exist begin with 1 centimeter, divide by 100, you get the thickness of a human hair, divide by 100 again, you get the wavelength of light. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 1,000, and you get the magnitude of these mirror motions. 1,000 times 100,000 times 10,000 times smaller than the wavelength of the light that you're going to use to detect this? That's ridiculous. 1 trillion times smaller movement than the wavelength of light? That's totally ridiculous, so I thought. But then I had long conversations with Ray Weiss and with Vladimir Braginsky in Moscow, Russia, and I became, during that period, well, during the period from 1968 to the fall of the Soviet Union in 1991, I built a very tight collaboration on research with Braginsky in Moscow and his experimental group. And I shuttled back and forth between Moscow and Los Angeles regularly, spending a month a year or a month every year in Moscow. And then you can ask me about that if you want, and the CIA and the KGB. But I had a very interesting period through the Cold War. But anyway, from these discussions with Ray and with Vladimir, and from reading Ray's marvelous paper, I told you he hadn't really published it. He didn't think you should publish a paper about this until you had detected gravitational waves, which came nearly 50 years later. And so he just put it in an series of internal MIT reports. But anyway, I read it finally. I became convinced, and I decided then, having become convinced that this was so important, so exciting for physics and astronomy and our understanding of the universe, that I would do everything I could as a theorist to help Ray and the experimenters to make this a success, to detect these gravitational waves. There was one particular challenge that I worked on, and my research group worked on hand in hand with Braginsky's research group from the late 1970s until today, and the two groups are still collaborating on that. And this is the following problem: that what you have to do ultimately in order to have the noise low enough that the signals will stand up really strong and be really clear, monitor the motion of 40-kilogram mirrors to a precision that is the same as the so-called half-width of the Schrodinger wave function of the center of mass degree of freedom of the mirrors. What that means is that the center of mass of the mirrors fluctuates randomly due to quantum effects, the kind of quantum effects you see in atoms and molecules, never before seen on a human scale, fluctuates enough that those fluctuations are at the level of the motions that the gravitational waves will cause. And so for the first time, and this is associated with applying the Heisenberg uncertainty principle to a 40-kilogram object, an object the size of you and me, and to astrophysical accuracy. And so the issue then was that the first time humans would see human-sized objects behave according to the laws of quantum physics and not classical physics. And so we had to develop what's called quantum non-demolition technology to deal with this. The idea is you try to get a gravitational wave signal through these moving mirrors, fluctuating mirrors, without these random fluctuations from quantum physics destroying the signal in the process. So it's a non-demolition of the signal. As we go forward, in fact, over the next decade, 2 decades, LIGO will be doing this at levels very small compared to these quantum fluctuations. So we have to have this quantum non-demolition technology very robust, which it is today. It will be installed for the first time in LIGO next year in order to deal with this. So I had great joy working with the Russians on this, and also living in the Soviet Union during the Cold War. In 1979, I got fed up with my collaborators on the experiment being, well, at MIT and in Russia. And so I convinced Caltech to build its own research group in experimental gravity. And we imported Ronald Drever from Glasgow. Ron Drever had made some major improvements on Ray Weiss's design for these gravity wave detectors, and a guy named Stan Whitcomb from the University of Chicago to lead this new group. We built, I should say, Ron and Stan and his team built a 40-meter interferometer of the Weiss design with the Drever improvements on the Caltech campus. That's 1% the length that we needed to have success, but it was a prototype. And there were other prototypes being built around the world. In parallel, Ray Weiss led a study at MIT of what it would take in practice to build a 4-kilometer interferometer. What were the issues that you would face that would be new, and could you really do it, and how much would it cost? And in 1984, with the results of his study and the prototype research and development under our belts, we proposed to the National Science Foundation the Ligo Project for Laser Interferometer Gravitational Wave Observatory. In 1989, we submitted then a proposal for constructing LIGO, which was a major, major project. We would first construct facilities, which would take about 6 years. Then we would build an initial set of these gravity wave detectors, these interferometers. Then they would probably not see anything. They wouldn't be sensitive enough. And then we would build advanced interferometers that would probably see a lot of stuff. And this is what we told the National Science Foundation. We told Congress that it was so hard, these instruments would be so complex and so hard to build that it would take going in 2 steps like this to have success. NSF bought this, Congress bought this. Once Congress had bought in, both the Republicans and the Democrats backed us to the hilt from 1992 when they bought into it until today, with no major budget cuts anywhere along the way. And they're very proud of it because, of course, we have had some success. And so, in fact, this is the way we did it. We built the first initial interferometers in the 2000s. We built the facilities in the 1990s, initial interferometers in the 2000s, ran them, didn't see anything. Built the next phase of the interferometers, the advanced interferometers, between 2010 and 2015, turned on and made a discovery, which I will get to in a moment. But first I want to say that in order to do this, we had to expand LIGO to a much bigger team than Caltech and MIT could possibly do together. So under the leadership of Barry Barish, a superb physicist who's the greatest designer and manager of big projects I think that physics has ever seen. He designed the collaboration that pulled this off. And it's now a collaboration of 1,000 scientists at 75 institutions in 15 nations. And he led us through the early phases of this. And I just want to hammer home that this really is now a big project with a lot of people. I'm going to show a few of the people. If you look at these pictures, you will see that most of these scientists are not much older than you are. They're graduate students or postdoctoral students, most of them. And this is really the future of this field and of many fields. It's your generation that are pulling this off. This is the Caltech group at present, the MIT group. The group, we have 2 gravitational wave detectors of this sort. One is in Livingston, Louisiana. These are the people there. One in Hanford, Washington. These are the people there. I've just given you 4 out of 18 institutions, 4 out of 80 institutions, 1 country out of 16 countries that are now collaborating on this. Now, a few words about my own personality. I hate working in big projects, but this had to be done big. There was no way it could succeed otherwise, but I don't like it. I prefer to work with a few students and maybe another colleague professor like Brzezinski or Ray Weiss. It was great fun until we went big. We had to go big, and I did everything I could to make this succeed. But by the early 2000s, I had trained enough young theorists who could take over what I was doing that I got out. But I got out partly for that reason. I wanted elbow room. I wanted to be able to do my own thing. By contrast, I'd say the majority of my colleagues, the majority of physicists really enjoy working in a big collaboration, and they enjoy the excitement of it and the camaraderie of it. It's just that I'm an introvert who pretends to be an extrovert when I'm in public. So the second thing that happened is in 2001, I became very worried that the community of computational physicists and astrophysicists did not have the capability to simulate the sources on computers, the sources of gravitational waves we were going after. And that meant that when we saw signals come in, we wouldn't know how to interpret the signals. We needed to have simulations on computers that predicted shapes of waves, gravitational waves, that could then be compared with the observations in order to through that comparison, to pull out information about what the source was doing, what it was and what it was doing. And although people had been working since the 1960s on trying to develop these simulations of colliding black holes in particular, it was not going well at all. And so I at that point, left my day-to-day involvement in the Ligo Project. I created at Caltech a project doing computer simulations. Just as I'm not an experimenter, though I did everything I could to help the experimenters, I'm also not a computational physicist, though I did everything I could do to help them. I provided vision, direction, and joyfully pulled information out of the simulations. But I teamed up with Saul Tucholsky, the guy who, as a student of mine decades earlier, had developed the theory of black hole vibrations. I teamed up with him to develop, to build something called the SXS project for simulating extreme space-times, which itself then became a 15-year effort to bring these simulations to a point where we could simulate colliding black holes at the level of accuracy that was needed by LIGO, and do it fast enough to keep up with the data that come in from LIGO. And so we now have that capability, and that's crucial. And now I will turn to the discovery, which I'm nearing the end of this, and this is the exciting part. On 14 September 2015, a year ago, we discovered gravitational waves for the first time. After all this effort, for me and for Ray Weiss, a 50-year effort, a half-century effort. And I'm going to tell you what it was we saw. And I'm beginning with a computer simulation of the source that we saw. So we saw the signal in gravitational waves. We compared with the computer simulations to see what the source was, and then we went in, and from the computer simulations we inferred just what the source was doing. And here is the story. 1.3 billion years ago, in a galaxy far, far away, two black holes that you see here as shadows. It's their shadow they cast against a field of stars behind them. Two black holes were going around and around, creating this swirling appearance because they bend the light rays that come from the stars, and so as they go around and around, the light rays come in different directions as they go around and around, create this swirling pattern through what we call gravitational lensing. As those black holes went around and around, approaching each other, they emitted gravitational waves, and that drove them to collide right there and merge. It wasn't very spectacular, you think at first sight, but in fact the simulations say it was so spectacular that it converted 3 solar masses of black hole mass into gravitational wave energy. That is the same thing as you would get if you took 3 suns and annihilated them completely, and then took all the energy that you get out and converted it into gravitational waves. And that burst of gravitational waves came so quickly that the power that came out in a unit time, the energy that came out in a unit time, the power, was 50 times bigger than the luminosity of all the stars in the universe put together. 50 universe luminosities during the collision in a fraction of a second, all in gravitational waves. No light was seen, no X-rays, no radio waves, nothing, just gravitational waves. We wouldn't have known this had happened if we didn't have a gravitational wave detector. We're seeing sides of the universe that have never been known before. Those gravitational waves then propagated out from the galaxy in which those 2 black holes resided. They traveled across the universe through intergalactic space. They arrived at the outer reaches of our galaxy 50,000 years ago. Just to set it in perspective, when the waves were emitted 1.3 billion years ago, multicelled life was just forming on Earth when that happened. No humans, nothing except single-cell life up until now, and multicell life was just forming. They arrived at the Earth 50,000 years ago when our ancestors were sharing the Earth with the Neanderthals. Or, I'm sorry, they arrived at our galaxy, the outer edge of our galaxy 50,000 years ago when the Neanderthals were still here. They arrived at the Earth on 14 September of last year. They arrived first initially at the Antarctic Peninsula. These waves propagated up through the Earth from the Antarctic Peninsula, unscathed because they're so penetrating, up and passed through our gravitational wave detector in Livingston, Louisiana, and 7 milliseconds, 7/1000 of a second later, passed through the gravitational wave detector in Hanford, Washington. Here is the signal that was seen in Livingston. There's the signal that was seen in Hanford, the raw signal. For people who know about such things, bandpass filter to remove noise above 350 hertz and noise below 35 hertz where the detectors are noisy. Otherwise, it's just the raw signal. You see it by eye. When it was cleaned up, it looked like this. And by comparing with the supercomputer simulations, we inferred that one black hole weighed 29 times as much as the sun, the other weighed 36 times as much as the sun. The final black hole was 62 times as much as the sun. 3 solar masses went into gravitational wave energy. Now I was able to explore geometric dynamics for the first time. Remember I said that was a goal. Here is what this black hole collision looked like according to the simulations if you look in from the 5th dimension. And so each black hole is a sort of a trumpet horn going down. And the 2 black holes go around and around. And I'm going to pause the movie as they get close, and I'll slow it as they get close into slow motion. The color coding depicts the slowing of time. Time flows very slowly in the red region deep out in there. The black region is inside the black holes. You'll see some black region in a minute. And they are beginning to merge, and it's creating a veritable storm in the fabric of space-time, a splashing wave like a giant ocean wave during a storm in the ocean. And this is what's producing those 3 solar masses of gravitational wave energy. Then it dies out and it's done. It was a very brief but very violent storm. So for the first time now, we are seeing both observationally and in simulations the geometric dynamics, how warped space-time behaves in a storm. A few words about the future and then I will quit. The sensitivity of these detectors will be continually improved over the coming years and decades. Within the next 3 years, we expect to see also neutron stars that have a size about the size of Dublin or smaller, that they're heavier than the sun. The central regions of those neutron stars are 10 times more dense than the nucleus of an atom. They spin on their axes, and little mountains on their surfaces should produce gravitational waves. These also emit electromagnetic waves called pulsars. We'll watch black holes tear neutron stars apart. We'll watch neutron stars collide. We will watch supernova explosions. We will look for gravitational waves from what are called cosmic springs, and we'll have great surprises. We will have 3 other windows onto the universe open up. Ligo looks at gravitational waves that have periods of a millisecond. Another detector called LISA will look for gravitational waves with periods of minutes to hours. Another technique called pulsar timing arrays, gravitational waves with years to decades. And then something called the CMB polarization, gravitational waves from the Big Bang itself, watching the birth of the universe, that have periods close to the age of the universe. The biggest lessons from my career that come from all this are, first of all, prepare broadly. All that training I got in engineering, in experimental physics, and theoretical physics was very important. Watch for unexpected opportunities and grab them. Work hard and persevere. It's a 50-year perseverance for me, but it's been a marvelous experience. Thanks.